Hey everyone, Miss Lee here. Right before the video gets started. So as I was editing this video, I realized it was pretty long and it was meant to be kind of a short video just highlighting a couple skills. So if you already know how to do some of these skills, like if you already know how to solve systems by substitution and you just want to know how to do it by elimination, you can use this title card here with different timestamps to help guide you through where you can skip along the video to just help make this more efficient. So enjoy the video. Hey everyone, welcome back. So in this video, we're going to be going over how to solve systems of equations algebraically, and we're going to be focusing specifically on linear equations. This is a really important skill to have not only in Algebra 1, but in 8th grade math, and then if you go on to higher levels of math, you're actually going to see this in calculus and in linear algebra as well, just in slightly different forms. Now, even though we're dealing specifically with systems of linear equations, these methods are applicable for more complex systems later on. So if you're dealing with quadratic linear systems or quadratic systems, you can still use these methods. Now, going into the video, you might need a few things. So you can find these notes and print them out on my website, just so that it's easier for you to follow along. You're also probably going to need a TI-84 just to help with any quick calculations. In addition, whenever you see a green slide, that's going to be an opportunity for you to try out the skill on your own and have the opportunity to see the answer. So I highly recommend that whenever you see a green slide that you pause the video there, and I'll also give instructions when you see that. So before we can even go into solving systems, we should first define what a system of equations is. And a system of equations is two or more equations that share variables. And so when I say that they share variables, so in each equation you're going to have the same variables, you're going to see the same letters throughout the system. So in my first equation I have an x and a y, and in my second equation I also have an x and a y in this example over here. In addition, what's cool about a system is that the value of each variable is equivalent throughout the equations. So let's say that in this first equation that x equals 4, in your second equation x would also equal 4, right? And so whenever we're solving systems, this is really, whoops, I should probably do it in a color that we can see. This is just finding intersection points. Right? So for each of these equations over here, we can actually graph them, so we can visually represent them on a graph. And when we solve the system, the intersection points of those two curves, of those two lines, would actually be our solutions to our system. So whenever we're solving a system, we are finding intersection points. Solutions and intersection points for a system are equivalent terms. So whenever we're asked to solve a system algebraically, and the main reason why I'm covering this is because let's say that you're taking a state exam like the algebra regents, for certain questions it will ask you to solve using a specific method, so solving specifically algebraically or specifically with elimination, substitution, right? But when we're solving systems algebraically, that means that we're either using the elimination method or the substitution method. Now, they're slightly different. So whenever we're doing the elimination method, we're really adding or subtracting to eliminate a variable to 0. So we're trying to get rid of a variable. And the reason why we're doing this is because it turns our system with multiple variables into just one equation with one variable, so it's a little bit easier to solve. So let me just show you how I would do that with this example really quickly. So in this example, I have two equations, two different variables, but I see that if I add these equations together, then 4x plus negative 4x, that actually is 0, right? 4x plus negative 4x equals 0. So that is eliminated. And what I'm left with is 8y plus 2y, which is 10y, equals 20 plus negative 30, which is negative 10. And that looks like a pretty easy equation that I can solve for. And so that's the whole reason why we would do elimination. We're trying to get the system into something that's a lot simpler to solve. Now, when we're dealing with substitution, it's a little bit different. So we would solve for one variable and then substitute the expression that our variable equals into the second equation, right? So for this example, right, we have that y equals negative 2. So I can actually just substitute this expression, or this constant negative 2, into my second equation when I see y, right? So when I do that, I get 4x minus 3, and then instead of writing y, I'm going to substitute in that value, negative 2, that I have equal to y in my first equation. And then write the rest of my equation out. I can multiply negative 3 and minus 2 together to get 4x plus 6 equals 18. And once again, I get a linear equation with one variable that's actually pretty easy to solve. So the effect of both of these algebraic methods is actually the same. We're turning our complicated problem of a system with multiple variables into a simpler problem of one equation with just one variable that we can very easily solve. Just the steps before it are slightly different, but the effect is going to be the same. So let's go into our first example of solving systems by elimination. And something that I like to tell my students is that whenever we're solving systems by elimination, you can always remember how to do this by remembering this acronym MAS. So the first letter of this acronym, M, stands for manipulate. So you want to manipulate one of your equations or both of your equations just so that the coefficients of one of your variables is the same. And remember, when I'm talking about coefficients, I'm talking about the number that's in front of a variable. So when I'm looking at my coefficient for my coefficient for x and my coefficient for x in my second equation, right? My coefficient for x in my first equation is 5, right? And then my coefficient for x in my second equation is 10. So when I think about those coefficients, I know that the least common multiple of those coefficients is going to be 10, right? And so I don't actually have to do anything to the second equation. I just have to do something to this first equation to change it so that this coefficient becomes 10. And so what I can do is I can just actually multiply this entire equation by 2 so that my coefficient changes. So when I do that, I get 10x plus 2y. Remember, I'm distributing the 2 throughout this entire equation to create an equivalent equation, equals 18, right? I know that these two are equivalent because I could just divide by 2 on both sides of the equation and then end up with my original first equation over here. Now, I didn't do anything to my bottom equation, so I'm just going to bring that right underneath. So there are definitely other ways to go about this, right? There's no one right way to manipulate your equations. The end goal is just to make sure that the coefficients for one of your variables is the same. And we want to make sure that we're doing this in the least amount of steps possible just because we don't want to be doing too much work. And also, when you add more steps, you're more likely to make a mistake. So we want to make sure that we're doing this in the most efficient way possible. Okay, so now that I have my new system, what I want to do is go on to my next step, which is add or subtract my equations together in order to eliminate that variable. So I have 10x plus 2y equals 18, and I have 10x minus 7y equals negative 18, right? And I notice that I can get rid or eliminate this x variable over here because I have the same coefficient for both of them. So once I do that, I want to think, should I add my equations together or subtract my equations together in order to eliminate this to 0? And I know that 10x minus 10x would equal 0, so I'm going to subtract my equations together. So I'm subtracting this entire equation from the first one. And so when I do that, my x's eliminate, and then I have 2y minus negative 7y. And so remember, whenever you're subtracting a negative sign, you actually have to add these two coefficients together. So when we do that, we get 9y equals 18 minus negative 18. Once again, same kind of thing. Whenever you subtract a negative, it's like you're adding instead. So we have 18 plus 18, which is 36. Okay, so now that I've subtracted my two equations together, I can actually just solve this equation here because it's a linear equation that is pretty simple to solve. So I have 9y equals 36, right? I can solve for y by dividing 9 on both sides, so I'm doing that inverse operation. And so I end up with y equals 4. Okay, now I want us to look back at our original system, right? We have two different variables. So we have two unknown values. I only found the value for one of my unknowns, so I only found it for y. I need to find what x is as well. But now that I know what y is, what I can do is I can just pick one of my equations, doesn't matter which one, and I can just substitute in this value for y in order to solve for x. So I'm going to pick my first equation over here because I just think it's going to be easier to use. So I'm going to take 5x plus y equals 9. But I know what y equals now, right? Y equals this value 4, so I can actually substitute that in. So I have 5x plus, and I like to substitute in parentheses just in case my value is negative, right? And so when I do that, I can subtract 4 on both sides to solve for x. So I get 5x equals 5, right? When I have 5x equals 5, I can just divide by 5 on both sides to isolate x, and I get x equals 1. So I found my x value and I found my y value. And remember how I said that intersection points are the same thing as solutions to systems? So I can actually write my solution to my system as a coordinate because it would represent a point. So remember, whenever I'm writing a coordinate, I write my x value first. So this would be 1, comma, and then my y value, 4. And so this would be my solution to my system. So take a minute and try this one on your own. And when you're ready to check your answer, you can unpause the video. You solved it on your own. You're ready to check your answer. Let's check it together. So I know that I need to manipulate my equations, right? I don't really see an easy least common multiple between 2 and 7, right? If I were to use my least common multiple of 14, then I would actually have to multiply both of my equations by something. But I actually noticed that this 3y over here, right, and this 1 over here, my least common multiple is just 3, right? So I can just multiply my entire first equation by 3. So I'm going to multiply this by 3. And so when I do that, I get negative 21x plus 3y equals negative 19 times 3, which is negative 57. Okay, and then I didn't do anything to my bottom equation, so I'm just going to bring it down. Okay, so now I have a variable where the coefficients are equivalent, so I have 3 and 3 over here, right? So all I want to do is add or subtract in order to eliminate that variable with the equivalent coefficients. So I have, I'm just going to write it down over here so it's a little bit easier to work with. Equals negative 57, whoops. And then I have negative 2x plus 3y equals negative 19. Okay, so I think I can subtract these, right? I can subtract this bottom equation so that my y's cancel out. And so 3y minus 3y is just 0, right? Negative 21x minus negative 2x, remember whenever you subtract a negative, it's like you're adding. So negative 21 plus 2 is negative 19x. And this equals negative 57 minus negative 19, right? And remember, whenever you subtract a negative, it's like you're adding. So negative 57 plus 19, which is negative 38. Okay, so now I get a linear equation that's pretty simple to solve. So I have negative 19x equals negative 38. I can just divide each side by negative 19, and then I would get x equals positive 2. So remember, I'm not done. Now that I know what one of my unknowns is, I can leverage that in order to help me find my second unknown, which would be y in this case. So I just need to pick one of my equations. I'm just going to pick the top one because I think that would be easiest, but you can really choose any of them and it should work out. So I'm going to pick my top equation, negative 7x plus y equals negative 19. And now I'm going to substitute. So this is the s part of my mass. So I have negative 7x, negative 7 times 2. And remember, I like to substitute using parentheses, plus y equals negative 19. This is negative 14 plus y equals negative 19. Let me write it over here. And then I can add 14 on both sides, once again, using my inverse operations. So I have y equals negative 5. And then whenever I am writing my solution to a system, I can write it in coordinate form. So my x would go first, so it would be 2, comma, negative 5. And that would be my solution. Okay, so now that we know how to solve systems using one algebraic method, elimination using the mass technique, we can try using the substitution method now. And the way that I like to remember this is something called the PS3 method. So it's P and then 3 S's, so I thought it would be catchy if it was called PS3. Anyway, it's pretty similar in terms of its reasoning for why it works, right? And the end result for what we want in order to be able to solve the system, right? We want to use this method in order to get something that's pretty easily solvable. So let's try it out, right? So for the substitution method, the first thing that we want to do is just pick the variable that we want to solve. The easiest way to go about picking this is you want to pick the variable in your equation that has a coefficient of +1, right? A +1. And in my first equation, I see that my y variable has a coefficient of +1. Remember, when I don't see a coefficient, the secret coefficient that's hiding there is 1. Now, if you do not have a variable with a coefficient of +1, then you want to find a variable where you can easily divide out or multiply out by another number so that it can become +1, right? In this example, in my first equation, because my y has a coefficient of +1, that's the variable that I'm going to solve for. So this is what I'm going to solve for. So I don't even have to worry about my second equation right now. I'm just going to focus on my first. So I have -4x plus y equals 6, and I want to solve for y. So I'm going to add 4x on both sides. I get y equals 6 plus 4x. Great. So now that I know what y equals based on my first equation, remember that your y value is equivalent in both equations in your system, right? So I can actually take this expression that I just solved for y, the 6 plus 4x, and substitute that into my second equation whenever I see a y. So in my second equation, I have -5x minus y, but instead of writing y, I'm going to open up a parentheses and then substitute in that expression that I just solved y for. And I'm going to bring over the equals 21 because I didn't do anything to it. Okay, so let me try to simplify this a little bit. I see that I have to distribute my negative sign, right? So I have -5x minus 6 minus 4x equals 21. All right, I can simplify this a little bit more. I have some like terms over here, so I can simplify this -5x and this -4x. So I end up with -9x minus 6 equals 21. Okay, and that looks like a pretty easily solved linear equation for me. So let me just write it over here. So I'm just going to add 6 on both sides, keeping up with my inverse operations. I have -9x equals 27. I'm going to divide by -9 on both sides, and then I get x equals -3. All right, so just like how I had when I was doing the other method, when I was doing elimination, I only solved for one of my unknowns, so I need to solve for my other unknown. And you can pick any equation and then substitute in that x value and solve for y. I'm going to pick up this first equation over here just because I think it's going to be simpler. So I have, let me change the color. I have -4x, but instead of writing it in x, I'm going to substitute in that value, x over here, and then copy everything else over so that I can solve for y. So then this becomes 12 plus y equals 6, and I'm going to subtract 12 on both sides, so then I get y equals -6. Okay, and then once again, I can write my solution as a coordinate, so this would be -3 comma -6. So all I had to do was pick the variable that I want to solve, and I pick it based on whether or not I have a variable in my system that has a coefficient of +1. Then I want to solve for that variable. I want to substitute that expression it equals back into my equation, my other equation, and then I want to substitute in my value to find my other unknown. So now you have a check for understanding. So you can pause the video here, try this out on your own, where you can try out the PS3 technique, and then when you're ready to check your answer, you can unpause and press play. All right, you did your work, you're ready to check your answer. Let's try it together. So when I look at my system over here, I want to pick the variable that I want to solve for, and I see that this y over here actually has a coefficient of +1. And if you remember your last check for understanding, this is actually the same system, right? So we can actually tell pretty easily whether we're on the same track, whether or not we're getting the same values as the last time we did this check for understanding. We're just doing it using a different method, right? So this y over here has a coefficient of +1, so that's the variable that I'm going to solve for. So I'm going to highlight that just so that I know. So this is what I'm solving for. Okay. So I have -7 plus -7x plus y equals -19. I'm going to solve for y, so I'm going to add 7x on both sides. I get y equals -19 plus 7x. Great. So now I can take this expression that I just solved for, this negative 19 plus 7x, and I can actually just substitute it into my second equation for y. So I have negative 2x plus 3, and instead of writing y, I'm going to substitute in this negative 19 plus 7x. And then this equals negative 19. Great. So now I just have to distribute. And so I get negative 2x, and then this is minus 57 plus 21x equals negative 19. Okay, looks like I can combine some like terms. So I have 19x minus 57 equals negative 19, and then I can add 57 on both sides. So I get 19x equals positive 38. I'm going to divide by 19 on both sides. And so let me get rid of this because it's a little bit messy. And so I would get x equals positive 2. And then if I think back to my last check for understanding, I did get that x equals positive 2 the first time as well. So it looks like I'm on the right track. So now that I've solved for x over here, I can now solve for y. So once again, I'm just going to use that first equation because it's going to be simplest. I have to just do less steps. So I have negative 7, and instead of writing an x, I'm going to substitute in a 2. Plus y equals negative 19. I get negative 14 plus y equals negative 19. Add 14 on both sides, and I get y equals negative 5, which matches the same y value that I got for my first check for understanding. So my solution is going to be 2 comma negative 5. And I've solved my system, this time using the substitution method. So before you leave to go do some extra practice problems where you're going to practice the skill, I just want to leave you with a couple key points. So a lot of students that I've worked with have had a really hard time mastering the algebraic methods for solving systems of equations because they get kind of confused with the difference between elimination and substitution, because ultimately they are really similar. They both ultimately create one variable linear equations that we can very easily solve. That's the point of using these methods, right? They both operate under your properties of equality rule, so ultimately you're going to get the same result whether you use one method over another. And in some situations it may be easier to use elimination versus substitution or the other way around. And so the biggest takeaway that I want you to have after watching this video is that there are 2 main algebraic methods for solving systems, and you can very easily remember both of them by using this acronym MAS for elimination or PS3 for substitution. And if you need extra help in understanding those methods, you can go back to earlier in the video so you can see those examples and checks for understanding again. So hopefully this was helpful to you. If you have any questions, as always, feel free to check out my website or give me an email, and good luck.